will talk to us from Tehran and I cannot see the title now. Okay, I have to continue. 6 points of initial self-embeddings of models of arithmetic. Welcome.
Thank you. Thank you. Hello, everyone. First, I want to thank Roman for giving me the chance to talk here. In this talk, I'm going to speak about my joint work with Ali on 6 points of initial self-embeddings of models of fragments of arithmetic. The story begins with a paper by Harvey Friedman in 1973. The paper is titled Countable Model of Set Theory. In this paper, Friedman kind of rediscovered the notion of standard system for admissible set theories. This notion was introduced by Dan Scott in 1960s, I think. But Friedman, by discovering the importance of this notion, proved many important results on countable models of set theory in this paper. And the one which is of our interest is that every countable non-standard model of Peano arithmetic and he proved that every countable non-standard model of finite set theory, which is bi-interpretable in Peano arithmetic, is isomorphic to a proper initial segment of itself. Actually, he proved a more general result. But before going to that more general theorem, let's fix our notation together. We are living in the language of arithmetic. We have the arithmetical hierarchy. And I think most of you are familiar with arithmetical hierarchy. And, sorry. And with the fragment, and as most of you know, the fragment, we have fragments of I sigma n and I pi n, in which the induction axiom is restricted to sigma n formulas or pi n formulas. And by x, we mean the formula which asserts the totality of exponentiation function. And for every level of arithmetical hierarchy, for example, for every natural number n, we have the satisfaction predicate for sigma n formulas in the theory of I delta naught plus x. Moreover, when we are in the theory of I sigma 1, this satisfaction predicate is we know about its complexity. The complexity of set of sigma n for every n larger than 0 is sigma n, and the complexity of set of delta 0 is delta 1. Then we show the Ackermann's membership relation by this formula, and we have the restricted form of overspill in every model of fragments of I sigma n. In other words, for every sigma n formula and every proper cut, if phi holds in every element of I, then these phi overspills I. That means there exists some elements larger than m, for which phi holds for every element of m smaller than m. We show the for every model y sigma n, we show the set of sigma n definable elements of m by this notion k n of m. And when we have a model of Peano arithmetic, we show the set of all definable elements of m by k of m. And it is folklore that Kn of m is sigma n elementary substructure of m for every model of I sigma n. And by a cut, we mean an initial segment with no last element, and we have a strong cut, the notion of strong cut. A cut I is called strong if the Ramsey theorem, the infinite Ramsey theorem holds in the cut for M. Or equivalently, if the cut is strong, if for every coded F in M, whose domain includes I, there exists some element A of M such that the interval between I and A is devoid of any element of F of I. And at last, we have the notion of I standard system for every cut, which is the family of those subset of I which are of the form of intersection of I with a definable subset of subsets of M, and then we have the standard cut instead of I. We omit the subscription, and easily we write standard system of M. It is well known that the necessary and sufficient condition for a cut to be strong is that the two-sorted model of I and I standard system of M is a model of ACA 0, in which the second order theory of ACA naught is the theory whose models are of the form of M and A, such that these M and A is a model of PA, and then all of these, the elements of A are unary predicates. We add them as unary predicates to the language, and A is closed under arithmetical definition. Then by an initial embedding, we mean an embedding whose range is an initial segment of the codomain. And when the range is a proper initial segment, we call that initial embedding a proper initial embedding. And when the initial embedding is between two sorted models, we call it a second order initial embedding if the embedding preserves elements of A and B. And when in general we have a self-embedding J, by I fix of J, we mean the longest cut whose elements are fixed by the self-embedding, and fix of J is the set of all fixed points of M by J. It is straightforward to prove that fix of J is a sigma 1 elementary substructure of M, and and every self-embedding fixes all sigma 1 definable elements of M for a model of Y sigma 1. Now we are done with the basics and we can go into the history. As I mentioned, Friedman in his paper proved a more general result. The result was about if we have two countable non-standard model of Peano arithmetic, then the necessary and sufficient condition for embedding a model, the first model into the other initially is that they have the same standard system, and the sigma 1 theory of the first one is subset of the sigma 1 theory of the second one. Moreover, in 1982, it was proved that if these two models share a cut, that the cut itself is a model of PA, and if M and N share have the same I standard system, and if the sigma 1 theory of M with parameters from this I is a subset of sigma 1 theory of N with parameters from this I, we can make this J to fix all the elements of this I. And if we take both of these theorems are proved by back and forth method. And if we take a close look to the proof of Hayek-Pudlak theorem, we realize that we don't need the whole strength of PA here. It is enough that I satisfy the totality of exponentiation function, and it is enough for M and N to be countable non-standard model of I sigma 1. Afterwards, Rousseau in 1987 proved that for every fragment of for the fragment I sigma 1 of PA, every countable non-standard model of I sigma 1 do have a proper initial self-embedding, and moreover, these proper initial self-embedding with their fixed points help in characterizing models of I sigma 1 between all countable non-standard model of I delta 0. In other words, a model of I delta naught is a model of I sigma 1 if and only if for every element of M there exists some proper initial self-embedding such that it fixes this self-embedding fixes all elements smaller than A. 10 years later, Tanaka generalized Rosser proof for one direction of Rosser theorem for the second order theory of WKL0, which is the second order theory whose models are model of I sigma 1 if that A is closed under delta 1 definability and big Koenig's lemma holds in the model. I hope everything is I hope that everything is clear so far. And do you hear my voice? Because I don't see anything.
Everything's fine.
Oh, okay, okay.
So let's go on. Quick question about the Tanaka result.
Yes, please.
Is this a second order embedding in the sense that you defined earlier?
Yeah, this is a second order embedding. Yeah.
Thank you.
Welcome. Thank you for your question. And up to here, these are the only results about the fixed points of initial self-embedding, or at least these are the only results about fixed points that I have seen in the literature. But when they turn into the realm of automorphisms, especially automorphisms of countable recursively saturated models of Peano arithmetic, there are many beautiful results about their fixed points. For example, Sprinsky in 1982 proved that if I is closed, if a cut is closed under exponentiation, then it can be realized as I fix of J for some automorphism J. Or in 1991, it was proved that for a cut, the necessary and sufficient condition for a cut to be realized as the set of fixed point of some automorphism is that cut to be strong and it to be elementary substructure of M. In the same paper, it was proved that if the standard cut is strong in M, then we can find some automorphisms of M such that that automorphism fixes as minimum as possible of elements of M. So the question that came to mind was that can we modify these three results for initial self-embedding of models of arithmetic? And it turns out that the answer is positive, and we can modify all of these three results for countable models of I sigma 1, and we don't need recursively saturation condition. And instead of these automorphism, we have proper initial self-embedding. In the rest of this talk, I'm going to talk about these three modifications. The first main theorem of this talk is about those cuts that are closed under exponentiation. And the theorem states that if M is a countable non-standard model of I sigma 1, then the necessary and sufficient condition for I to be realized as I fix of j of some initial self-embedding of m, and even a proper initial self-embedding of m is that I to be closed under exponentiation. Because of the time restriction, I'm going to omit the proof of implication 1 and 3 to statement 2, and I'm just going to concentrate on the construction of proper initial self-embeddings in this talk, in all of the theorems that I will state. So suppose that I is closed under exponentiation, and we want to see how we will build proper initial self-embedding. Our method is based on back and forth method, and is a combination for this theorem is a combination of Smerinsky's theorem and the proof of Friedman theorems for that proof that was in casebook, in chapter 12 of casebook. Just a reminder here, by B sigma n is denoted for the collection of the axiom of collection for restricted to sigma n formulas. Since for we are in the model of I sigma 1, and I sigma 1 implies B sigma 1, so we can use B sigma 1 in the model, and because we have the satisfaction predicate for delta naught formulas, and by getting help of sigma 1 over spill, we can find some B such that this B will serve us as an upper bound for the range of the initial self-embedding that we are going to build. So we can find some these B such that for every element of I and for every delta naught formula, when we have a sigma 1 formula, we can bound its existential quantifier with these B. We will have a 3-level back and forth for building the initial self-embedding that we want. The first level is for making the domain equal to M, as usual, like usual back and forth methods. The second level is for making the image a proper initial segment of M, and the third level serves for making I to be exactly I fix of J. So our strategy is to build finite tuples of U bar and V bar of elements of M, such that for every elements of I and for every delta 0 formula, this formula holds. This formula somehow says that the sigma 1 type of this U bar is equal to sigma 1 type of V bar, and this B is a bound for the range of the proper initial self-embedding. So this statement in orange would be our induction hypothesis, and at the end of the proof, we huddle all of these finite U bar and V bars together to have a proper initial self-embedding. And just a short remark here: if we had just two level of back and forth, then the initial self-embedding that we would gain would fix all of elements of I. But we need the third level to make I to be exactly equal to I fix of J. So let's go to details of every level of back and forth. The fourth level is for making M equal to the domain. I have put the induction hypothesis here for convenience, and because M is countable, we can enumerate elements of M y1 and check every element of M if it is already in the domain or not. For example, if C is arbitrary element of M and it is not already in the domain, we define the subset of I H like this, which somehow represent the sigma 1 type of U and this C with parameters from I. Since set of delta naught had the complexity of delta 1, so this set is sigma 1 definable, so it is coded in M by some H, and for every S in I, every segment of this H is coded by some H of S in I. This happens because I is closed under exponentiation, and since S is in I, so the code of every subset of I is in I as well. So we write the definition of H of S here formally. Here this formula just asserts the definition of H of S here. By quantifying out this C, we would have a sigma 1 formula here, whose free parameters is just H of S, which is in I, and U bar. So by taking a look into induction hypothesis, we can have the same formula for V bar. So there exists some Y, some Y is, we have here we have a sigma 1 formula for V bar and for H of S, which is in S. This formula holds for every S in I, and this formula is sigma 1, so we can use sigma 1 over spill and find some element larger than I and find some Y in purple, such that this formula holds for this Y. This Y can, it is easy to see that this Y can serve as an image for this C. So this C is in the domain of M. The next level of back and forth is for making the range a proper initial segment. So again, we check elements of M y1 and we check those elements of M which is smaller than elements that are already built and that are already in the range of the initial self-embedding that we have built up to now. Again, like the previous slide, these L somehow represent the sigma 1 type of V bar and D with parameters from I, and again it is sigma 1 definable. So every segment of this L by elements of S intersected by elements of I is coded in I. So we claim that for every S in I, this formula holds. Afterwards, since if this claim is true, then we can use pi 1 over square and we can find some X which serves as inverse image for this D. How will we prove this claim? Suppose it is not true. So there exists some S in I such that the negation of this formula holds. So here we have a sigma 1 formula with free parameters L of S, which is in I, and U bar. So again, we can use induction hypothesis, and we have this formula for V bar. Since this happens for we have the universal quantifier here, and since D is smaller than maximum of V bar, so this formula holds for D. But this is in the exact, in this formula exactly contradicts the definition of L of S, which states that if R and I is in L of S, then for every z if sats of delta not holds, then z is larger than b, but here this contradicts this formula. For the third level of back and forth, our trick until now we have built an initial self-embedding that fixes all elements of I. We want I to be exactly equal to I fix of j. So we fix a downward cofinal sequence in the set m minus I, like this set. Then in every level of induction, like suppose we are in the level kth of our induction, we consider ek. We want to find some element of m smaller than ek, such that its image is not equal to that element. If we find such an element in M, then since this sequence is downward cofinal, we have the desired property. For this purpose, for every S in I and for every X smaller than ek, we define such a set which represents sigma 1 type of U bar and X with parameters I which are smaller than S. It is clear that this set is sigma 1 definable. Then we define f of S, the sigma 1 definable function of f of S from elements smaller than ek to elements smaller than 2 to the s plus 1 in this way. Then since ek is larger than I, and since I is closed under exponentiation and S is in I, so ek is larger than 2 to the S plus 1. So we can use sigma 1 pigeonhole principle, which states that if we have a sigma 1 function whose domain is larger than its codomain, then the function cannot be one-to-one. So f of S for every S in I cannot be one-to-one. So there exists the distinct US and US prime smaller than ek, such that fs of US is equal to fs of U prime S, US prime. What does that mean? This means by taking a look at this, to this f of S and this set R, this means that the sigma 1 type of U bar and US with parameters I smaller than S is equal to sigma 1 type of U bar and US prime with parameters from smaller than S. On the other hand, this statement in green can be rewritten as a sigma 1 formula. So by sigma 1 over spill, we can find distinct elements U and U prime smaller than ek, such that these U and U prime have the same sigma 1 type with U bar and parameters from I. This U in purple here is the element that we want to show that we will find an element in M which can be the image of U and it is not equal to U. For this purpose, we iterate the fourth level again for u and u prime, for u and u prime, and we will find v and v prime such that induction assumption holds for u bar, u prime, and v bar, v and v prime. Since v and v prime are distinct, so u is if u is equal, if u is not equal to v, so we can serve as the image for this u. And if it is equal, if this v is equal to u, since v and v prime are distinct, then this v prime can serve as an image for this u. And we are done with this proof. I hope everything is clear here, and if any question, please do ask me. Okay. Here we have a generalization. Here we have a generalization for theorem A, which states that for every countable non-standard model of WKL0, the theorem, we can find the necessary and sufficient condition for cut to be realized as I fixed of j of some second order initial self-embedding of m and a is that I to be closed under exponentiation. I'm not going to go through the details of this proof. It has a similar proof, but we need some tricks here to preserve the elements of this A. But the gist of the proof is same as theorem A. Now we have the second main theorem of this talk, which states that the necessary and sufficient condition for a cut to be realized as the set of fixed points of an initial self-embedding and even a proper initial self-embedding for a countable non-standard model of I sigma 1 is that cut to be strong and to be a sigma 1 elementary in M. Again, our concentration is on the construction of these proper initial self-embedding. Here, our construction is based on, we don't use a back and forth method here. We build our proper initial self-embedding here based on ultra power construction, Geifman ultra power construction. In his famous paper, Geifman represented his ultra power construction. Here I have picked those part of the theorem that we need for our purpose. So suppose that M and A is a countable model of ACA0, then there exists some elementary end extension NQ of M, in which this subscription Q is the set of rational numbers with its natural ordering, and there exists some copy of this Q in the set of N of Q minus M, along with a composition preserving embedding hat from the family of self-embeddings of Q into the family of self-embeddings of N of Q, such that it has 4 nice properties that we need for our construction. These nice properties are that the M standard system of N of Q is equal to this A, Moreover, if H is a fixed point free self-embedding of Q, then the set of fixed points of H hat is equal to this M, and this copy of Q prime is downward cofinal in NQ minus M, and every upper bound for H of Q, for every self-embedding H of Q, if Q, every isomorphic copy of every upper bound is also an upper bound for H hat of N of Q. Moreover, if H is a proper initial self-embedding of Q, then H hat is a proper initial self-embedding of N of Q. So we are going to use this theorem for building our initial self-embedding. Now we have all the ingredients. So suppose that M is a model of I sigma, is a countable model of I sigma 1, and I is a proper cut of M, which is strong in M, and which is sigma 1 elementary in M. Since I is strong in M, as I mentioned in preliminary section, I, an I standard system of M, is a model of I sigma I naught. And as we saw in the previous slide, this is the only assumption that we need for Geifman theorem. So there exists some elementary end extension of this I, which is denoted by N of Q, whose I standard system is equal to I standard system of M. And there exists a copy of Q, which is called Q prime, which is downward cofinal in this green part here. Now take a look at this picture here. If you remember from the beginning of this talk, I mentioned Haken-Pudlak theorem. That I said the theorem said about if we have two countable models of I sigma 1, and if they both share a cut, and if they have the same I standard system, and if the theory of the sigma 1 theory of the first one with parameters from this I is a subset of the sigma 1 theory of the second one with parameters with this cut, then by Haken-Pudlak theorem that I put in this box, we will have an initial embedding from M into NQ, which fixes all elements of I. So consider this initial segment of N of Q, which is the range of F. And pick an arbitrary element of F of M like M0. Since Q prime is downward cofinal here, we can find an element of Q prime like CQ0 in smaller than M0. Now for this Q0, we can find some fixed point free self-embedding of H such that this Q0 is an upper bound for the range of H of Q. So H hat is a proper, by Geifman theorem, H hat is a proper initial self-embedding of N of Q, and its range is an initial segment, which I have shown it by this light blue, and it is smaller than M0. So H hat of F of M, H hat of the image of H hat on this initial segment that I have magnified it here, is a subset of F of M. Moreover, we can define J to be equal to the composition of these F inverse to H with H hat and F, and this J is well defined. And this is an proper initial self-embedding of M, because this F inverse of M0 is an upper bound for its image. So the only thing that we need to prove about J is to prove that fix of J, the set of fixed point of a J is equal to I. Since this H hat is fixed point free, so fixed point by Gauss theorem, fix of H hat is equal to I, and this F preserves all of elements of A fixed. So it is easy to see that fix of J is equal to I. And we are done with the proof of this theorem. And then again, we can generalize this result for the second order theory of WKL0 and gain some second order proper initial self-embedding for those ions which are strong and which are sigma 1 elementary substructure of M. Again, the proof is similar to theorem B, but we need some delegation to preserve elements of the second sort. And at last, we have the final main theorem of this talk, which states that if M is a countable non-standard model of I sigma 1, then the necessary and sufficient condition for existence of some initial self-embedding and even a proper initial self-embedding which fixes as minimum as possible of elements of M is that N to be strong in M, the cut N to be strong in M. Sorry. Again, here for building proper initial self-embedding, we use back and forth method. But here, our back and forth is more delicate than the one that we used in proving theorem A. First, let's fix some notation. By this capital F, we mean the family of all sigma 1 definable partial function of M. And when we have a sigma 1 partial function F, then if it is defined by a sigma 1 formula like this, in which this delta is a delta naught formula, then by this notation here, we mean an abbreviation for this sigma 1 formula. And if it has a superscript by less than W here, we mean that all the bounded quantifiers, all the quantifiers are bounded by this W. Again, exactly like the method that we used in proving theorem A, we can find some element of M like this B in purple that will serve as an upper bound for the image of initial self-embedding. And our back and forth method in this back and forth method, our strategy is that to build finite tuples U bar and V bar that satisfy two conditions. The first condition is P of U bar and V bar, which this property states the exact property that we had in theorem A. This means that U bar and V bar have the same sigma 1 type, and this P is an upper bound for the image. We just changed the notation for convenience. And the second property guarantees that if we have any undefinable element, then its image would be different from that element. So, to be more exact, it says that if for every partial sigma 1 definable partial function, if f of u is not sigma 1 definable, then f of v should be different from f of u. And if this f here is the identity function, then for every sigma 1 for every undefinable element, its image would be different from that element. Here I just explained the fourth level of back and forth, and the second level is similar to the fourth level with minor differences. So here again we are going to enumerate elements of countable m and check elements of m one by one and see if they are already in the domain or not. For this purpose, let's just take a look at this fact that states that if we have a model of I sigma n, and in particular I sigma 1, and if we have a set of formulas, which we call a type, such that all of these formulas are sigma n, and if the Gödel number of this set of formulas is coded in M, then this type is realized in M. This fact holds because we have the satisfaction predicate for sigma n formulas, and since sigma n over spool holds, so we can find realization of it is straightforward by using these two facts. It is easy to find realization of P of x. So let's see, be an arbitrary element of M. We define the type P of x whose realization would serve as an image for this C. So we define P of x, this type, in two parts. The first part is serves for guaranteeing that this U bar and C bar and V bar and any realization of this P1 satisfy the first property in the induction hypothesis that I stated in the previous slide, and the second part of the type serves for guaranteeing that the property Q, the property of Q for U bar and C and V bar and any realization of these P holds. So if X, this purple X is any realization of this P, it can serve as an image for this C. By this fact, first note that all of the formula in P is sigma 1 formula. This one is delta naught, this one is delta naught, and this one is sigma 1. So we have a sigma 1 set of formulas. We need to prove that this P is coded, and moreover, it is finitely satisfiable, which means it is a type. The first part, the P1, is coded because this part is sigma 1 definable, so it can be coded in the model. But for proving that the second part is coded as well, what we do, we have, I have put the P2 here again for look, whenever we need it, we can look at it. Since the family of sigma 1 partial function is countable, we can enumerate it like this, and we define the subset of n natural the subset of natural number b like this. It states that any j is in B if fj this formula for fj fj of u and c holds, and fj of u and c is sigma 1 definable. If we take a look at P2, we realize that if we prove that this B is coded, or it is in standard system of M, because the standard system is an algebra and is closed under completion, so it's the completion of this B would be in the standard system. So, and the completion of this B is exactly the definition of this P2. So our task is to prove that this B is in the standard system. For this purpose, we define the set R, the subset of N2, that is a sigma 1 definable subset of N2, which states that elements of R is pair of I and J, such that the Fj of U and U bar and C, this formula for Fj of U bar and C holds, and Fj, this means Fj of U bar and C is in the K, is sigma 1 definable. Why this holds? Because every elements of K1 of M, every sigma 1 definable elements of M is of the form of some Fi of 0. It is of the form of Fi of 0, such that Fi as this formula holds for Fi of 0. So since this set is sigma 1 definable, it is in the standard system, and B is equal, every J is in B if and only if there exists some natural number such that the pair of I and J is in R. So B is definable with a parameter in the standard system. On the other hand, since N is strong, so N and standard system of M is a model-wise ACA 0, and by the definition of ACA 0, it is a standard system of M is closed under arithmetical definability, so B is in the standard system, and therefore its completion is in standard system, so P2 is in the standard system, so it is coded. So the only thing that is remained to prove is that P is finitely satisfiable. I have put the definition of P here again. Suppose P is not finitely satisfiable. So there exists a finite number of formulas in this type which for there is no realization. In other words, there exists some natural number, or there exists some least natural number, such that for this K, there exists K plus 1 many elements of F and another elements of F, such that there is no these three statements just is saying that there is no realization for the formulas in P, which consist of these F and these G's. After that, by shedding a lot of sweat, we can find a partial sigma 1 function H in F, such that these three statements hold when we substitute F by H, and when we substitute these K plus 1 many LGs with just many of them, then these three statements hold. So clearly the minimality of K is denied. So we have proved that P is finitely satisfiable. I hope it has been clear. This was the last proof for this slide, for this talk. And what are the open problems in this area? In 2006, Ali proved a conjecture by James, which states that if we have a countable recursively saturated model of Peano arithmetic, in which the standard cut is strong, then every elementary substructure of M is isomorphic to some to set of fixed point for some automorphism J. Then the question that arises is that can we modify this theorem for countable non-standard model of I sigma 1 and sigma 1 elementary submodel of M, and instead of automorphism we have proper initial self-embedding or not? More generally, in the same paper, Ali proved that if I is a general cut, not just standard cut, every I-coded elementary submodel of M, in which I-coded, I have put the definition of I-coded here, is realized as a set of fixed point of an automorphism. By an I-coded set, I mean that the set there exists an element that the set is equal to the I part of that sequence. Again, the question that we can propose is that can we generalize this theorem? Can we modify this theorem for proper initial self-embedding or not? That was it. Thank you for your attention, for your time.